Okay, so today we are looking at aligning agentic world models via knowledgeable experience learning. This one's from researchers at Zhejiang University and UCLA.
Right.
And this paper, it really tackles what they call the modal disconnect in embodied AI.
Which is basically why your smart agent knows the recipe for a salad, but then tries to slice a tomato without even picking up a knife.
Exactly. So they introduce this framework, WorldMind, that solves this, but not with massive fine-tuning. Instead, it lets the agent build its own world knowledge repository on the fly during inference.
It's a really cool approach. Instead of treating failure as, just a loss function to minimize back-end training, WorldMind is built on this idea of predictive coding.
Okay.
The agent makes a guess about the physical world, it tests it, and if it's wrong, if it fails, that error becomes what they call an epistemic signal. It's a trigger to write a new rule. So it learns two key things.
The do's and don'ts.
The do's and don'ts. Process experience from its mistakes, those are the constraints, and goal experience from its successes, which are the heuristics.
And the results are pretty serious. We're talking state-of-the-art on EB-ALFRED and EB-Habitat benchmarks, huge reductions in these physical hallucinations.
And this is the killer feature.
Yeah.
The ability to transfer this learned knowledge, this sort of physics textbook, from a big GPT-4 model to a smaller GPT 3.5 model.
And it just works.
It just works. Instantly improves the smaller model's performance without updating a single parameter.
Yeah.
It's training-free alignment.
Wow.
That's the overview. Now, we should really dig in because this gets at a problem that has been, plaguing this field since we first tried to put LLMs in robots.
The brain in a vat problem.
The brain in a vat problem,
Yeah.
exactly. You have these models with just incredible semantic knowledge. They've read the entire internet.
Right.
If you ask GPT-4, how do I clean a lamp? It gives you a perfect logical sequence. Find a cloth, wet the cloth, wipe the lamp. Semantically, it's flawless.
But physically, it's totally ungrounded.
Totally. Because in a giant text corpus, sliced tomato and used knife are statistically close. They're related. But the model doesn't get that holding the knife is a hard physical precondition for slicing.
It just sees them as semantic neighbors, not a strict causal chain.
And that is the modal disconnect. The model gets the why and the what, but it completely fails on the how that physics imposes. So it generates these plans that sound great in language, but are just errors in a simulator.
Like trying to grab an apple that's inside a closed drawer.
Exactly. In the LLM's vector space, get apple is a perfectly valid next step. But in the physics engine of the simulator, it's just an impossible action.
And the typical fix for this, what we usually reach for in the industry, is either supervised fine-tuning or reinforcement learning.
SFT or RWL, yeah.
You just try to beat the physics into the weights of the model.
Which, it works, but only to a point. The authors here argue that it's just fundamentally inefficient for these big open-ended worlds.
Why is that?
Because when you use SFT or RL, you're trying to compress all these dynamic, complex environmental rules into static model parameters. You're basically baking the layout of one specific kitchen into the neural weights.
So the model becomes brittle.
Super brittle.
You move the robot to a new house where, the drawers have latches instead of handles, and suddenly those static parameters just fail.
And you have to retrain or fine-tune again. It gets really expensive.
So WorldMind just flips this on its head.
It flips it completely. It asks, can we just freeze the model parameters and instead let the agent learn the physics of its specific environment on the fly? It's a shift from, say, memorization to active inference.
This is where they bring in Carl Frister's work on predictive coding, which I love. It's so cool seeing cognitive science theory actually get implemented in an engineering paper.
It's a perfect fit for this problem. The whole idea behind predictive coding is that intelligence isn't just about passively soaking up data. It's an active process of minimizing your prediction error.
So the brain, or in this case the agent, is a prediction machine. It's constantly projecting a model of what it thinks should happen onto the world.
Exactly. So instead of the agent just blindly saying move forward, it first has to predict, okay, if I move forward, my location coordinates are going to change by X.
If it walks into a wall instead?
That's a prediction error. And in standard deep learning, we usually treat error as, noise or loss, something bad you want to get rid of. But here, that error is pure gold.
It's a signal?
It's an epistemic signal. It tells you something fundamental about the environment. The agent thinks, okay, I predicted movement, but I got a collision. Therefore, this space in front of me must be solid.
It basically turns the agent into a little scientist running experiments. My hypothesis is that I can walk through this wall. Nope. Okay, write that down.
And that writing it down is the world knowledge repository. the WKR. That's the memory structure they build. And like we said in the intro, it stores two different kinds of experience. Let's break down process experience first, because that's what stops the hallucinations.
These are the don'ts, the guardrails.
Right, the don'ts. Process experience comes entirely from those prediction errors. And the whole mechanism runs on this simple loop: predict, act, verify.
Okay, so walk me through a cycle of that.
All right, let's say the agent's goal is to open the fridge. Step one is state abstraction. It looks at the world, but, and this part is really important, it doesn't look at the raw pixels.
Right, because pixel noise isn't causal, lighting changes, camera jitter. That would just confuse it.
It would get totally lost. So it abstracts the state into these high-level descriptions. Things like door, closed, hand, empty, lock, engaged.
Got it.
Step two, judgment. It predicts that the outcome of the action open fridge should be the new state door, open. Then step three is execution. It sends the command.
But let's say the fridge is locked, the arm pulls, and nothing.
The verification module sees that mismatch. Prediction was open, reality is closed. That failure triggers the self-reflection module. The agent basically hits pause and asks itself, okay, why did that fail?
And because it's a powerful LLM, it can look at that abstracted state, specifically at the lock, engaged variable, and figure it out.
Correct. It synthesizes a new rule. It creates a new constraint in the WKR that says something like constraint, cannot execute open on fridge if status is locked.
And that rule effectively becomes a stand-in, a surrogate model for the actual physics engine.
Yeah, that's a great way to put it. The next time it wants to open the fridge, it can just query its own repository first, see the rule, and know it has to find a key or unlock it first.
It aligns the semantic plan with the physical reality it just discovered.
Yep.
But knowing what not to do is only half the battle, right? You can follow all the rules and still just wander around in circles.
Which is where goal experience comes in. The do is. The heuristics.
And this comes from success, not failure.
Exactly. While process experience is learned from failure, goal experience is distilled from success.
This is interesting because so much of machine learning is focused on the errors. How does it learn from a successful run?
So when the agent finally completes a task, let's say heat the soup, WorldMind goes back and analyzes that whole trajectory, the full history of actions.
And the first successful run is probably messy.
Oh, it's super messy.
Yeah.
It probably checked the bathroom for a microwave, opened the wrong cupboard 3 times. It was just exploring.
Right.
WorldMind is designed to filter out all that noise. It looks for the critical path. It distills that successful, messy sequence down to a core meta instruction. Something like, to heat soup, go to the microwave. Or, to find a knife, check the countertop first.
Ah, so it creates a shortcut for next time. It prunes the search space.
It prunes the search space, exactly. It stops the agent from exploring semantically bizarre areas. If the goal involves cooking, the goal experience repository essentially tells it, hey, don't even bother looking in the bedroom this time. It biases the policy towards the optimal path.
So process experience stops fatal errors. Goal experience drives efficiency.
That's the combo.
Now, I want to ask about the implementation. This predict, act, verify loop with a self-reflection module. It sounds computationally heavy. Are they running this for every single action the agent takes?
That would be a latency nightmare. Imagine simulating the physics of the entire room just to walk across it. No, they use this really clever optimization they call gated simulation.
Gated simulation, how's that work?
The agent only triggers that heavy simulation and verification loop when the object it's about to interact with is grounded.
Grounded? You mean it's visible or its location is known?
Yep. So if the agent just navigating, just doing a move ahead action to get from the hallway into the kitchen, it bypasses the simulation. It just trusts its default policy.
But the second it intends to interact with something,
the gate opens. The moment the plan involves pick up apple or sliced tomato, the whole verification system kicks in.
That makes a lot of intuitive sense. I don't need to simulate physics to walk down a hallway, but I definitely need to pay attention when I'm about to use a knife.
It focuses the compute where the risk of a physical hallucination is highest. It's a great balance between the cost of inference and the need for safety.
Let's talk numbers. They benchmarked this on EB-ALFRED and EB-Habitat. For anyone listening who isn't deep in embodied AI, these are simulators for household tasks. Clean the lamp, cool the lettuce, things like that.
Right, and the performance jump was really significant.
Yep.
On EB-Habitat, using GPT 4.1 Mini as the backbone LLM, the raw success rate, the SR, jumped from about 41% with a standard React baseline to over 50% with WorldMind.
A 9 or 10% absolute gain in this field is a huge leap.
It's massive.
Right.
But there's a nuance in the metrics I think is really important. They don't just report success rate. They also report goal condition success, or GC.
Right. Why the two different metrics?
This is critical for understanding how the model is getting better. Success rate is binary. Did you complete the entire task, yes or no? If you do 99 steps perfectly and then drop the object at the end, you get a 0.
Yeah.
Very harsh. But goal condition success measures process adherence. Did you find the object? Did you go to the right room? Did you pick it up correctly? And WorldMind showed even bigger gains in these GC scores than in the raw success rate.
So even when it fails that final binary check, it's failing better. It's following the right procedure.
It's following the right procedure. It proves that the goal experience heuristics are working. The agent is on the right track. It's not just making up some nonsensical plan anymore.
Speaking of failure, the ablation studies had this really counterintuitive result in their error analysis. The timeouts actually went up.
Yeah, that one's interesting. Usually in robotics, if you see timeouts increasing, you think your agent is just getting stuck or confused. But here, it's actually a positive signal. It's a sign of resilience.
How so?
Okay, think about the baseline agent. It tries to walk through a closed door. The physics engine says collision. It tries again. Collision. After a few tries, the episode just terminates as an invalid action. The agent is dead in 5 seconds.
It fails fast.
It fails fast. WorldMind, on the other hand, hits the door, stops, reflects, updates its WKR with a new rule, and then tries a different route. It stays alive. It keeps exploring.
So it's not running out of time because it's stuck. It's running out of time because it's actually trying to solve the problem instead of just crashing immediately.
It died of curiosity, not stupidity. It massively reduced the invalid actions, the direct physical violations, even if that meant it took longer to think about its next move.
I love that framing. Okay, we have to talk about the cross-model transferability. For me, this is the most mind-blowing part of the whole paper.
This is where the fact that the World Knowledge Repository is symbolic really shines. Because the WKR is just text. It's a list of rules and constraints written in plain English. It's totally model agnostic.
Physics is physics. Gravity pulls things down. It's true whether you're GPT-4 or GPT 3.5.
Precisely. So the researchers ran this amazing experiment. They had a GPT-4 agent run around the environment, make mistakes, and build up a WKR. It basically wrote a textbook called How to Survive in This House.
And then they just handed that textbook to a GPT 3.5 agent.
They gave it to a GPT 3.5 turbo agent, which is, significantly weaker and much more prone to hallucination. And instantly, the GPT 3.5 agent's performance just skyrocketed.
Wow.
It didn't have to learn the hard way that the stove is hot. It just read the rule that GPT-4 had already written down.
That's like intergenerational learning for robots. The smarter model can do the risky exploration, and then the cheaper, dumber models can just reap the benefits.
And here's the real kicker.
Yeah.
It also worked in reverse. They took the WKR generated by the dumber GPT 3.5 and gave it to GPT-4. And GPT-4 still got better.
Wait, really? How?
Because a fact is a fact. Even a less capable model, if it bumps into a locked door, has discovered a hard physical truth. The door is locked is an objective piece of reality. GPT-4 can use that fact just as well as GPT 3.5 can.
This just opens up the door for fleet learning. You could have 1,000 cheap robots bumping into things in a warehouse, each uploading their little process experience failures to a central server.
And suddenly, the central brain, the big, super intelligent model, knows the exact physics of the entire facility without ever setting foot in it.
Shared world models.
Shared world models. It democratizes physical alignment. You don't need a massive compute cluster to simulate the world if you can just have a shared library of constraints.
They even push this further, right? With the embodied web agent experiment.
Yeah, that was a really tough task. The agent had to browse a website to find a recipe and then turn around and physically cook that recipe in the simulator. It's a huge modality switch.
From reading HTML to controlling robot arms, that's usually where these agents just break. The context switch completely destroys their grounding.
But WorldMind handled it.
Right.
Because the constraints are symbolic, they're portable. The rule, you need a knife to slice things, applies whether you're reading it in a recipe online or you're standing in the virtual kitchen.
And the results.
They doubled completion rates in some cases compared to the baselines. It really shows how you can decouple the world model from the agent architecture. The world model becomes this portable asset.
Which is just a huge deal for scalability, but I do want to throw a little bit of a wet blanket on this. The authors themselves touch on mechanism interpretability, and it raises a bit of a philosophical question.
I think I know where you're going with this. Just because the agent learns to avoid the glass door, does it actually understand the concept of glass?
Exactly. We see the performance go up, we can open the WKR and read the text rule that says glass is solid. But we don't really know how that bit of text mathematically shifts the decision boundary inside the LLM's latent space.
It's the Chinese room argument all over again.
Is the agent really simulating a world model in its head? Or is it just following an incredibly complex flowchart of if I see this text, then don't output that token?
If state description contains glass, do not output movement token.
Right.
It's functional alignment, for sure, but is it actual understanding? The paper proves we can align the behavior without training, but we might just be building a very, very sophisticated rule follower, not a truly grounded entity.
But if you're a factory owner, do you care? If the robot doesn't drop the expensive part on your foot, does it matter if it truly understands gravity or if it just has a rule against dropping things?
And that's the pragmatic take. For where we are right now, just trying to get these things to work reliably at all, WorldMind is a massive step forward. It bridges that semantic physical gap without the insane cost of RL training.
It turns failure from a cost into an asset. That, for me, is the core takeaway. Every time one robot fails, it gets smarter, and it writes that knowledge down for every other robot to use.
It's scalable, it's interpretable, because we can actually read the rules, and it's effective.
Well, we'll be linking the paper, Aligning Agentic World Models via Knowledgeable Experience Learning, in the show notes. It is a dense read, especially the appendices on the self-reflection prompts, but it's well worth your time if you're building agents.
Definitely check out the diagrams of the process experience loop. It really helps clarify the whole architecture.
Thanks for tuning in to AI Paper Podcast. Keep your gradients clipped and your world models aligned. We'll see you in the next one.